at the end. We have just a couple more topics to cover in Chapter 9, and those are counting and probability distributions. We touched on probability distributions a little bit in Chapter 8, but we're going to take a deeper look at it now. Let's talk first about a random variable. One of the questions in the general survey that we talked about earlier was, how much television per day do you watch? If the answer was 6 hours or less, we can assign a random variable x and divide that time period into 1 hour increments. So if I have x being the number of hours, 0, 1, and so forth, up to 6, I can express the number of people who responded with each of these by a function p of x. So I might have for 0, 0.10, 0.21, okay, and p of x then is our random variable. The definition is a random variable is a function that assigns a value to each outcome of a situation. So here's my random variable. And when I draw this table or make this table, this is called a probability distribution. I'm making just this table with the possible outcomes and the probability of each of them. These numbers in this row must add up to 1. So I've got 0.10, 0.21, so that would be 0.31. And this would bring it to 0.59, 0.76, 0.89, 0.95, and 1. So this is a probability distribution. Another thing that I do sometimes is to draw a graph called a histogram. And a histogram looks a lot like a bar graph. There are some distinctions. In a histogram, there is no space between the bars. So my first bar might be here, 0.10, pretty short little bar. Okay, we don't have any probabilities up here higher than 0.30, so this is enough. And then my bar for number 1, notice there's no space. This goes just above the 0.2. 0.28 would be just a little bit higher. 0.17, a little bit lower than this one. 0.13, higher than this, but not as high as this. 0.06 and 0.05, just very slightly less than 0.06. So this is a histogram for that information. Says, give the probability distribution for the number of heads showing when 2 coins are tossed. So we'll start off with x and p of x. And let's think about the possible outcomes when I toss two coins. I want to know the number of heads. It's possible there could be no heads. There could be one head and one tail, or there could be two heads. And if we are tossing a fair coin, we'd like to think the probability of no heads would be about 1/4, one head about 1/2, and two heads also 1/4. How did I get those? Well, let's look at the outcomes. If I toss two coins, I could have heads, 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 tails, tails, heads, or tails, tails. Tails, tails would go here. Heads, tails would go here. Tails, heads would also go here. And heads, heads would go here. So this shows how I got those probabilities. If I were wanting to draw a histogram for this, it would look like this. I'm just going to make this 0.25 and 0.50, since those are the only two probabilities I've got. 0, 1, and 2. So for 0, 0.25. For 1, 0.50. And then for 2, also 0.25. So there's my histogram. Find the probability that at least one coin comes up heads. Well, the only time that one coin doesn't come up heads is over here at the 0.25. So I got 0.50 and 0.25 over here. So the probability of getting at least one head, okay, remember that at least one means either I get one or I get two. So this would be 0.75. Pause the video now and work on checkpoint 1. Now I want to talk about expected value. In the case of tossing the two coins, we would expect, or we wouldn't be surprised, if we got one head most of the time. Now, getting one head one time doesn't mean anything about the next toss. It could end up being two heads or no heads, or it could be one head again. But it might be nice on something a little more complicated to figure out what the expected value is so that we can look at the risk of whatever the event is and decide if it's worth it. So in the case of the TV viewing that we talked about a little earlier, let's find the expected number of hours per day of viewing. And to do that, we're going to take the number of hours and multiply it by the probability of that number of hours. So my expected value of x is going to equal 0.10 times 0 plus 1 times 0.21 plus 2 times 0.28, and I'm just going to continue on. Try to be a little bit consistent here. Okay, when I multiply and add all that together, I get 2.4. So we could say on the average, the respondents to this survey watch about 2.4 hours of television a day. Pause the video now and work on checkpoint 2. Another place where we might look at expected value is when we're buying tickets for a raffle or maybe paying to play for a carnival game, looking at how much we have to pay to play against how much we might expect to win. So, in this example, a local symphony decides to raise money by raffling off concert box seats worth $400, a dinner for two worth $100, and 2 CD recordings worth $20 each. A total of 2,000 tickets are sold at $1 each. Find the expected value of winning for a person who buys one ticket in the raffle. So here my random variable represents things that I could win. And we're going to call this net winnings, which means the value of whatever I win minus the value of the ticket that I had to buy to win it. So let's take a look at the box seats, for instance. That's worth $400 minus 1, so $3.99. If I have a losing ticket, my winnings are 0 minus 1, so that's -1. So the net winnings of each prize times their probability will give us an expected value. So let's make a table here. Put X on top and then P of X. Okay, for the box seat, $3.99, and there's a 1 in 2,000 chance of getting that. The dinner for two, net winnings of $99, and again there was only one of those available, so 1 in 2,000. The recordings were worth $20, so the net winnings would be 19. But there were 2 of those. Okay, and then, of course, we have all of the losing tickets. So for those, the X would be -1. And the probability of getting that had 1, 2, 3, 4 winning tickets, so 1996 out of 2,000. So now we're going to multiply this times this times this, and so on. And I end up with 1460 over 2,000. That is negative, because this pretty much dominates my fraction. So this is about -0.73. So on average, a person who buys one raffle ticket is going to lose 73 cents. So if it's a good cause, maybe I'm willing to lose 73 cents for it. Pause the video now and work on checkpoint 3. I'm sure some of you have been involved in some kind of a friendly little bet like the one we're going to talk about in this example. Each day, Lynette and Tanisha toss a coin to see who buys coffee at $1.75 a cup. One tosses while the other calls the outcome. If the person who calls the outcome is correct, the other buys the coffee. Otherwise, the caller pays. Find Lynette's expected winnings. So we need to think about what are the situations. So let's make a little table. And the first line is result Okay, the result of flipping the coin is either heads or tails. And then our next line could be the call. And the call could be heads here and tails here. And then my next line is going to be, does the caller win? Okay, the caller wins when these two are the same. So here we would say yes, no, no, and yes. And then what's the probability? There were 4 situations. We're going to assume they were all equally likely. So probability of 1/4 each. As Lynette wins a $1.75 cup of coffee anytime the results and the calls match. So this and this would be wins. You win $1.75. Okay, she loses $1.75 if they don't match. So here we're going to lose, so we'll say negative $1.75. And here negative $1.75. And so when I take 175 times 1/4, and now we're going to subtract 175 times 1/4, subtract it again, and then add it again. And as you probably already suspect, this comes out to 0. So what are Lynette's expected winnings? 0. It's just for fun. She's not going to make any money on it. Pause the video now and work on checkpoint 4. A situation like we looked at in the last example is called a fair game because the probability of making money and losing money is equal. I'm sure that most of you know that when we go to, say, a casino and play casino games, those are not fair games. We don't have an equally likely chance to win or lose money. We act as if we do, but we don't. So we're going to go back and look at the American roulette wheel and talk about expected value there. An American roulette wheel has 38 slots. 2 of the slots are marked 0 and 00 and are colored green. The remaining slots are numbered 1 to 36 and are colored red and black, 18 of each color. One simple wager is to bet $1 on the color red. If the marble lands in a red slot, the player gets his or her dollar back plus $1 of winnings. Find the expected winnings for a $1 bet on red. Okay, for this bet, there's only 2 outcomes. You're either going to lose $1 or you're going to make $1. And let's see what the probability of each is. Losing $1. If I bet on red and it comes up either green or black, I lost my $1. So there are 20 non-red spaces out of the 38. And then there are 18 red spaces out of 38. So now I'm going to multiply -1 times 20 out of 38 plus 1 times 18 out of 38, which is going to give us -2 out of 38. Okay, and that is approximately negative 0.053. So I have a slight, it's likely that I'm going to lose a little money. If I do this over and over again, the winning and the losing is going to be pretty similar. Okay, there's only a small chance, lose about a nickel per turn. Okay, let's pause the video now and work on checkpoint 5. A lot of times when we talk about expected value, it's mostly in terms of carnival games or casino games. But there's also some business applications that we might want to think about. For instance, a real estate developer has 2 potential projects. With project 1, there's a 30% chance of earning $1.25 million in profits and a 70% chance of earning $1.1 million in profits. With project 2, there's a 25% chance of earning $1.45 million in profits and a 75% chance of earning $1.05 million in profits. Based strictly on expected value, which job should be developed? So we want to look and get the most bang for our buck, the most profit that we can. So we are going to need a couple of tables here. So we're going to call the profits a random variable, P of X, 1.10, 0.7, and 1.25 million, 0.3. So my expected value here is 1.1 times 0.7 plus 1.25 times 0.3, which gives us 1.145. For my second project, $1.45 or 1.05. The chance of the 1.45 is 0.25, and here it's 0.75. So again, I'm going to multiply 1.45 times 0.25 plus 1.05 times 0.75, and this gives me 1.15. So which one is the better risk? Very slightly this one. Okay, I say very slightly, $0.05 million, so $50,000. When I'm talking about $1 million, I don't know how important $50,000 really is to me. So I might want to consider some other aspects of these projects. Pause the video now, work on your last checkpoint, and then move on to your homework assignment. Pause the video now and work on checkpoint 6. There's one more example I'd like to look at before we close out this section. We're going back now to the social science survey, and it says the social science survey gives the table gives the probability distribution for the number of children of respondents to the 2016 General Social Survey for those with 7 or fewer children. So let's make our table. I guess if you have more than 7 children, then we'll put you in a separate category. So now we want to find the expected value for the number of children in the families of the respondents that answered this survey. We're going to have 0 times 0.281. And we'll just go on and multiply each of these pairs. And when I multiply that all together, I get 1.804. So we could say from the results of the survey that the average family has 1.804 children. Now we know that no family actually has 1.8 children, but that's just an average number that we can use for comparison perhaps with other countries, or maybe we want to divide this into different social economic groups and see if there's a difference in the number of children per family. This is the end of this section. You should be ready now to go on to your homework assignment.